Hello friends, I'm Dr. Gaurav. In this video, I will discuss about unsteady flow energy equation in thermodynamics. Contents are unsteady flow including mass and energy balance equation, application of unsteady flow energy equation. Unsteady flow, the process in which there is change in control volume with time is known as unsteady flow process. When an unsteady flow process is analyzed, it is important to keep track of the mass and energy contents of the control volume as well as the energy interactions across the boundary. Some familiar unsteady flow processes are the charging of rigid vessels from supply lines and inflating tires or balloons. Unsteady flow processes are usually fixed in space, but they may involve moving boundaries. As you can see in the diagram, in the first diagram, boundary is not moving, but in the second diagram, as the fluid enters the control volume, then the piston will start moving upward. So in unsteady flow process, there is change in control volume also, whereas in steady flow process we have studied that there will be no change in control volume. So when the fluid enters the control volume or open system, then there will be change in the properties of the control volume, that is in mass and energy of the control volume, and also there will be change in the properties of the fluid entering and exit the system in terms of internal energy, flow work, kinetic energy, potential energy, etc. So in this diagram the boundary will be fixed, and in second diagram there will be a moving boundary as fluid enters the control volume. Next is symbol used. C represent velocity in meter per second. Z is elevation in meter. Small g is acceleration due to gravity in meter per second square. M over dot represent mass flow rate in kg per second. M represent mass in kg. P represent pressure in Newton per meter square. Capital V represent volume in meter cube. W over dot represent rate of work done in watt. Q over dot represent rate of heat transfer in watt. Capital U represent internal energy in joule. Capital H represent enthalpy in joule. PV represent flow energy or flow work in joule. Ke represent kinetic energy in joule. Pe represent potential energy in joule. Symbol per unit mass. Small v represents specific volume in meter cube per kg. Small w represents work done per unit mass in joule per kg. Small q represents heat transfer per unit mass in joule per kg. Small u represents internal energy per unit mass in joule per kg. Small h represents specific enthalpy in joule per kg. P into small v represent flow energy or flow work per unit mass in joule per kg. C square upon 2 or small ke represent kinetic energy per unit mass in joule per kg. Small g into z or small p represent potential energy per unit mass in joule per kg. Most unsteady flow processes, however, can be represented reasonably well by the uniform flow process, which involves the following idealization. The fluid flow at any inlet or exit is uniform and steady, and thus the fluid properties do not change with time or position over the cross section of an inlet or exit. If they do, they are averaged and treated as constant for the entire process. Unlike steady flow process, unsteady flow process start and end over some time finite time period instead of continuing indefinitely. Therefore, in this section we deal with changes that occur over some time interval delta t, where small t represent time, instead of with the rate of changes per unit time, such as q is equal to q over dot into delta t. It means that if q over dot is having a value of 10 joule per second, now if we want to find out the amount of heat transfer after 50 seconds, the value comes out to be 10 into 50, that is 500 joule. So we can find out this value of Q, because usually the unsteady case is for a definite time period. So if we multiply the rate quantity with the time period, then we'll get the quantity. Similarly for W and del E. Del E is equal to dE by dt into delta T. Unit may be joule or kilojoule. Applying conservation of mass or unsteady process when the time interval is delta t. So the mass balance says that total mass entering the control volume during time interval delta t minus total mass leaving the control volume during time interval delta t is equal to net change in mass within the control volume during time interval delta t. So m over dot in minus m over dot out is equal to dmcv divided by dt, where mcv is the mass of control volume. So change of mass of control volume with respect to time. Unit will be kg per second. So this mass balance is in rate form in kg per second. If we want in without rate form, then the mass balance will be total mass entering the system minus total mass leaving the system equal to delta mcv, change in mass of control volume, where delta mcv is equal to m2 minus m1 for cv, that is final mass of control volume minus initial mass of the control volume. Next is energy balance equation. Applying energy balance equation for unsteady process when time interval is delta t. So in this case we will have energy in minus energy out, that is energy associated with the fluid entering and fluid leaving the system, is equal to change in energy of the system, that is control volume. It may be in joule or kilojoule. So we can write down this in rate form: Q over dot in plus W over dot in plus summation of all the fluid entering M over dot multiply with the terms H plus C1 square upon 2 plus GZ. C1 square upon 2 represent kinetic energy per unit mass, small h represent specific enthalpy, that is enthalpy per unit mass, and Gz represent potential energy per unit mass. So this is for the entering fluid. Entry fluid minus exit fluid will be equal to dECV divided by dt, where ECV is the energy associated within the control volume. So this represents the rate of change of energy associated with control volume with time. So this equation is in the rate form. If you want to find out this in without rate form, then we will multiply this whole equation by delta t, that is time interval. So we will get Q in plus W in plus summation of all the fluid having energy in terms of enthalpy per unit mass, kinetic energy per unit mass, potential energy per unit mass. So this is for the entering fluid. You have to all, if you are having two fluid or more than two fluid, you have to all the values, add all the values here. This is for the entry condition minus exit condition is equal to M2 E2, this is energy per unit mass, small e is the energy per unit mass, minus M1 E1, that is final energy of the system minus initial energy of the system means control volume. So again we can write down this one as in minus out. So here we have replaced this C1 square by 2 with the kinetic energy per unit mass, that is small ke, and Gz with the small p, that is potential energy per unit mass, where small e, that is energy per unit mass, is equal to small u internal energy per unit mass plus ke kinetic energy per unit mass plus p potential energy per unit mass is the energy of non-flowing fluid within the control volume per unit mass. When kinetic and potential energy changes associated with the control volume and fluid streams are negligible, as is usually the case, the energy balance above simplifies to, that is we are saying that the change in kinetic and potential energy is negligible. That means these quantity will be eliminated, because if you do in minus out, that will be negligible change. So we can eliminate this quantity, this one and this one. And also if you put the value of E in this equation, so you can also eliminate this quantity, because this is having the difference of final minus initial value. So again the change is negligible, so we can say that this will be eliminated. So what we get finally? Q in plus W in summation of M into H, summation of the enthalpy fluid with the all the fluid entering the control volume, minus this is for entering, this is for exit, will be equal to M2 U2 minus M1 U1 for the control volume. As you can see in the diagram, mass is entering and the mass is leaving, and we have considered W as the work done by the system or on the system. Q is the heat transfer, and this is the control volume. So we have write down this, we have taken this as our control volume. Next is application of unsteady flow energy equation. In this first is filling up of a bottle. You can see in the diagram we are having a bottle with, so what is the property of this bottle? You can see here the bottle is filled gradually, therefore it is the case of an unsteady system. So as the fluid is entering the system, and also there is change in the property of the control volume. So this is the case of unsteady flow. Whenever there is change in properties of the control volume, it will be corresponding to unsteady flow energy equation. Bottle is initially empty, so when mass is not entering the control volume, this bottle is empty and connected to a pipeline through wall, this is the wall, for being filled. Let us denote initial state of the system or control volume by subscript 1 and the final state by subscript 2. So 1 represent initial condition of this bottle and 2 represent the final condition of this bottle, that is control volume. As initially the bottle was empty, so M subscript 1 will be equal to 0 because 1 represents the initial condition and initially the bottle is empty and there is no exit from the bottle, so M out will be equal to 0 because you can see there is no exit, there is only entry. So for the when there is no exit of the fluid, in that case the mass of fluid going out of the control volume will be 0. Now if we apply the mass balance and it is not in form of rate, so we can say mass entering minus mass leaving will be equal to change in mass of control volume, and the change in mass of control volume, that is delta mcv, will be equal to m2 minus m1 for the control volume. So mass entry, there is only one entry point, so m in minus m out will be equal to m2 minus m1. As m1 is 0, so this will be 0 and m out is 0, sorry, m1 is 0, that is this value will be 0, and m out is 0, that is this value will be equal to 0. So what left? M in equal to m out. So mass entering the bottle is equal to final mass inside the bottle. Now we will apply the energy balance equation. This is the energy balance equation and again it is not in the form of rate. Assuming the kinetic and potential energy changes associated with the control volume and fluid streams are negligible and treating bottle filling process to be occurring in insulated environment, that is Q equal to 0 and no work interaction W equal to 0. As you can see in the diagram, we have considered this bottle as insulated, so there will be no heat transfer going away from the bottle and also there is no work interaction. So in this case, the value of Q will be equal to 0 and W will be equal to 0. So this will be 0 and this will be 0, this will be 0 and this will be 0. And we have also considered kinetic potential energy changes as negligible. So this quantity will be eliminated, this will be eliminated, this Ke and Pe will be eliminated. And we will replace this E with U because I have already explained you that E equal to U plus Ke plus Pe. When the Ke and Pe changes are negligible, we can eliminate this quantity. So what left? This equation will become this one. So there is only one entry of the fluid in the control volume. So we have M in H in minus M out H out will be equal to M2 U2 minus M1 U1 for the control volume. As initially the bottle was empty, so M1 equal to 0, I have already explained this to you, and there is no exit from the bottle, so M out equal to 0. So if you put this M1 equal to 0, M out equal to 0, you will get this equation. M1 M in H in is equal to M2 U2, but M in equal to M2. So we get H in equal to U2, that is enthalpy of fluid entering bottle is equal to final internal energy of fluid in bottle. Next is we are doing just reverse of the previous case. Now in this case we are emptying the bottle. So here we are having a bottle. Initially the bottle mass is m1. So fluid in the bottle is having a mass of m1. And after some time it is emptying, so m2 will be equal to 0. So after some time this bottle will be gets empty, so m2 will be equal to 0. As there is no fluid entering the system, so m in will be 0 in this case. So if you apply the mass balance, sum of all the mass entering minus sum of all the mass leaving will be equal to change in mass of control volume, that is m2 minus m1. As value of m2 equal to 0 and value of m in is also 0, so we get m out equal to m1, that is mass leaving the bottle is equal to initial mass inside the bottle. Now if you apply the energy balance, this is the energy balance and it is not in the form of rate, so this is without rate form energy balance equation. Again in this case we will assume kinetic and potential energy changes associated with the control volume and the fluid streams are negligible. That means this Ke and Pe and out Ke and Pe will be eliminated and this E will becomes U. And again we are considering that treating bottle filling process to be occurring in insulated environment, that is Q equal to 0 and no work interaction W equal to 0. So here Q and W equal to 0. So what left? mh in minus mh out, sum of all the value of enthalpy associated with the all the uh, fluid entering the system minus sum of all the enthalpy associated with the fluid uh, leaving the system is equal to m2 u2 minus m1 u1 for the control volume. So there is only one entry and one exit. So m in h in minus m out h out will be equal to m2 u2 minus m1 u1 for the control volume. H m2 equal to 0 and m in equal to 0. I have already explained this to you. If you put this in the above equation, you get m out h out equal to m1 u1. But as we have already proved this with the help of mass balance, this one m out equal to m1. So h out is equal to u1. Enthalpy of fluid leaving bottle is equal to initial internal energy of fluid in bottle. Thanks. Any questions you can write to me gaurav.citm@gmail.com.